In this tutorial, you will learn how to simulate a Verilog design using Vivado. We will simulate two kinds of circuits, combinational and sequential. For the combinational circuit, we use a half adder as an example. For the sequential circuit, we use a counter as an example. Let's start by opening Vivado. I'm using version 2022.1, but you can use a different version. If you do, the user interface may be slightly different. First, create a new project. Give it a name and choose a folder location to save it. Then, you can select the FPGA board you are using or directly choose the chip. I'm using a specific board, but for simulation purposes, it doesn't really matter which one you select. Click Finish to create the project. On the left side, select the Add Sources menu, then choose Add or Create Design Sources. Create a new file and name it half adder. Right-click on the file you just created and select Open File. You can start writing your code here. This is the Verilog code for the half adder implementation. It uses just two logic gates. Next, we can create a test bench file by selecting the Add Sources menu, then choosing Add or Create Simulation Sources. Create a new file named half-adder.tb to serve as the test bench. Right-click on the file you just created and select Open File. You can start writing your test bench here. This is the code for the test bench. We instantiate the half-adder module, and in the initial block, we assign values to inputs A and B based on the truth table of the half-adder. To run the simulation, click on the Run Simulation menu. The simulation waveform will open. Then you can save the waveform configuration so that it remains the same when you rerun the simulation. Here you will see the Scope tab and the Objects tab. The Scope tab shows the module hierarchy, which matches the structure of your source code. In the Objects tab, you can view the internal signals of the selected module. For example, you can delete the existing waveform and try adding it again by selecting the signals, right-clicking, and choosing Add to Wave window. You can also drag and drop the signals into the waveform viewer. Once you add the signals, you can rerun the simulation. In this example, we run it for 20 microseconds. You can zoom fit the waveform and move the yellow cursor to the beginning. Then zoom in to see the inputs we applied to the half adder. You can verify that the output matches the truth table of the half adder. You can also see that the input changes every 10 nanoseconds. Another useful feature of Vivado is RTL analysis. This allows us to elaborate the Verilog design into a schematic, so we can visually analyze the structure of our Verilog code. If you're interested in learning more about basic Verilog, RTL circuits, integrating an ARM processor with your RTL module as part of a system on chip, and working on a neural network project, be sure to check out my online course through the link in the description. By enrolling, you'll also be supporting this channel and helping to keep it running. Now let's continue with the simulation of the counter design. Select the Add Sources menu, then choose Add or Create Design Sources. Create a new file and name it Counter. Right-click on the file you just created and select Open File. You can start writing your code here. This is the Verilog code for the counter implementation. This is a 4-bit counter. The counter starts counting when the start signal is high. It counts from 0 to 5, then resets back to 0 and waits for the start signal again. Now set the counter as the top module by right-clicking on it and selecting Set as Top. Then click Open Elaborated Design to view the schematic, which you can analyze if needed. Next, we can create a test bench file by selecting the Add Sources menu, then choosing Add or Create Simulation Sources. Create a new file named counter.tb to serve as the test bench. Right-click on the file you just created and select Open File. You can start writing your test bench here. This is the code for the test bench. We instantiate the counter module and include a clock generation block, which generates a clock signal with a frequency of 100 MHz. This is because we set the clock period t to 10 nanoseconds. Next, in the initial block, we start by setting all input signals to 0. This helps prevent any undefined X logic values during simulation. Then we reset the counter. After the reset, we assert the start signal to begin counting. Set counter.tb as the top module and run the simulation. If you encounter an error like this, it's because the previous simulation is still open. To fix it, go to the menu, select File, and then choose Close Simulation. Run the simulation again. The waveform window will appear. Save the waveform configuration by going to the menu, File, Simulation Waveform, Save Configuration As. This way, it won't overwrite the half-adder waveform. Add the internal signals of the counter to the waveform viewer and run the simulation for 20 microseconds. Zoom in on the signals to verify the counter's functionality. It starts counting when the start signal is high and counts up to 5 before rolling back to 0. If you enjoyed this video, don't forget to like, comment, and share. See you in the next one.